Welcome. We're going to look at Lecture 19. We're not going to do the whole lecture, but the important parts. And Lecture 19 talks about solving systems of equations. This is probably not new to you. Just some basic terminology, which may be new to you. A system of equations is a collection of two or more equations, each containing one or more variables. A solution is simply a set of the value of the variables that satisfy the equation. Now you can have large equations with a bunch of variables and a bunch of equations. We're going to deal with systems of just two equations and two variables. A solution is simply then going to be an ordered pair that satisfies each equation. A system is linear if you start with two linear equations, which you can see in that first format. These are both linear equations because our variables are raised to the first power only. And then a solution set is the set of all ordered pairs that satisfy that system. Now remember, not every system has to have a solution. If it doesn't have a solution, it's called inconsistent, and we'll see that as we go along. All right. How do we solve equations? Well, if we're thinking of linear system, that's two lines, think of pictures. If you've got two lines, one possibility is that they intersect at one point. Then there's going to be exactly one solution, and the equations are independent. Okay? They're two totally independent lines that happen to intersect at one point, and there will be one solution. Another option is that you have two equations that represent the same line. Then the lines basically lie on top of each other, and we say that the equations are dependent because they depend on each other. And then finally, the lines can be parallel. In that case, there is no point of intersection, so there'll be no solution. The system is inconsistent. So how can we solve a system graphically? The easiest way is probably just by intercepts of each line. So we have two lines here. The first line, what are the intercepts? And I'll just quickly do them. We can see that if x is 0, or if y is 0 rather, x would be 4. And if x is 0, y will be 2. And you can check that out later. Okay? So we have the point 4, 0 and 0, 2. And just because I want to graph it consistently, let me get a nice straight line. Okay, so that's the first line. The second one, x minus y equals 1. Let's see, if x is 1, it looks like y will be 0. If x is 0, it looks like we get minus y equals 1, so y has to be negative 1. So 1, 0, 0, negative 1. And now if I draw this line, and let me use a different color, it looks like these two lines intersect right here at the point 3, 1. Okay? And how would I check that? If it's a solution, it has to satisfy both equations. So we'll check. First of all, 3 plus 2 times 1. Okay, 3 plus 2 times 1. I'm sorry, that's the point 2, 1. Can't read my own graph. So 2 plus 2 plus 1 does equal 4. And if I take the point 2, 1 here, 2 minus 1 does equal 1. So it is a solution, and it's the only solution, the point 2, 1. This system is independent. The lines are independent. The system is consistent. Okay? All right, second example. Now, let's look at this one. X minus y equals negative 1. If we look at the intercepts here, let's see if x is, if y rather is 0, it looks like x has to be negative 1. And if x is 0, y would be 1. Okay? And we check that out. We have negative 1, 0, and 0, 1. And we get the following line. I'm being a little bit lazy here. All right, how about the second line? let's see, if y is 0 here, I get negative 2x equals 2. It looks like x has to be negative 1. And if x is 0, 2y equals 2, 0, 1. Notice what happens. I get exactly the same line. Okay? And so this system is dependent. And any point on the line would be a solution. Okay, so it has an infinite number of solutions. Okay, does that make sense? It is consistent because there are an infinite number of solutions, but the system is dependent. All right, what about the third? Let's look at our intercepts here. 3, 0, and 0, 3 for the first. 2, 0, and 0, negative 2. Okay, so 3, 0, and 0, 3 looks like this. And then if I look at the second line, 2, 0, and let's see, I'm sorry, negative 2, 0. Negative 2, 0, and 0, negative 2, and look what happens. Our lines are parallel. Okay, how many solutions? No solutions to the system, nothing that satisfies both equations at once. We say that our system is inconsistent. So with a linear system, those are your three choices. And so one way to solve a system is by graphing. But as you can see, that's kind of a pain to do, so we would like to find better strategies. And so instead of solving graphically, we're going to solve systems algebraically. And this, I am sure, is familiar to you. I don't think I'm doing anything that's anything new and different than what we've seen before. Okay. This method of substitution simply says that you look at your system, you solve for one variable in terms of the other, then you substitute into the second equation, solve, and then go back and find the value of the other variable. And of course, the key step is always to check. You'll know if you've done it right when you check your answer. So just to make things a little bit simpler for us, let me go ahead and designate our equations as 1 and 2 so that I can talk about them easily without having to write everything down. Okay, what do I observe? It says to solve for one variable. And I could solve for any variable in either equation, but I think it makes sense to solve for x in equation 1. Why? Because I won't introduce fractions. I add 2y to both sides. Okay. Otherwise, if I solve for any of the other variables, I'm going to have to divide and I'll have fractions. So I'm going to solve for x in the first equation. Okay, get that a little bit better so you can see it. There we go. Okay. Second step, we will take that equation, and here's the substitute part, is to substitute into 2. Okay, so what do? Here's my second equation, and I simply replace x with its value. Okay, is that clear? I simply took this equation and replaced x with 2y plus 1. And that, of course, gives me an equation just in terms of y, and I can solve that. 8y plus 4 minus 3y equals -1, so that's step 3 is solving. And it looks like I get what? 5y equals, bring that over, -5, so y equals -1. Okay? And once I have that, then I will go ahead and plug that value of -1 into equation 2. I'm going to plug it back into either equation, but I'm going to go into equation 1 because I started with equation 2 in solving for y, so let's make sure it fits into equation 1. So I'm going to solve for x in equation 1. Okay, so y equals -1, so x minus 2 times -1 equals 1. X plus 2 equals 1. Looks like x equals -1 also. Okay, so I have my single solution. Now I want to see if it works. So the last step is to check. And I have to check in both equations. So in equation 1, I replace x with -1 and y with -1, and I get -1 plus 2, and sure enough, that equals 1. It satisfies the equation. It checks. Okay, equation 2, again, x is -1 and y is -1. That is -4 plus 3, and that is equal to -1, and it satisfies both equations. So we found the solution. It is a consistent system, and our solution is -1, -1. Okay, we'll stop right there and come back in a minute.